Those silent scratches on ancient stones are not random wear. They are the forgotten language of medieval builders, a code left behind in granite and marble. This video deciphers that code to reveal construction technologies lost to history. You will discover how these subtle tool marks point to advanced methods that defy our assumptions about the past. We will investigate why perfectly straight cuts appear where only hand tools should have been used, and what mysterious devices could create such uniform drill holes in solid rock. By the end, you will see these historic structures not as silent monuments, but as complex machines whose secrets are only now being understood. What does our modern world overlook when we walk past the craftsmanship of the past? A single groove on a granite block might seem like random damage, but when you see thousands of them arranged in perfect parallel lines, a pattern emerges. These are the deliberate signatures of the tools that shaped our world. Archaeologist Dr. Elena Vance describes them as the fingerprints of history, each one a tiny record of contact between a craftsman's tool and the stone. To understand these marks is to learn the language of medieval construction. We primarily find three types of these impressions. Chisel scores are short, sharp grooves left by pounding and prying. Drill holes are the circular channels, often surprisingly deep and uniform, left by rotary tools. And then there are saw cuts, long, straight incisions that sometimes stretch for feet across a hard surface. The story is not just in their shape, but in their subtle variations. Look closely at a series of drill holes. Some might be shallow and rough, while others are deep and perfectly cylindrical. This difference is not a mistake, it is evidence. It can tell us that two different drills were used, perhaps generations apart, or that a single tool was being pushed to its limits. A change in the angle or depth of chisel marks can reveal where one team of workers handed off the project to another, each with their own distinct technique. These silent witnesses tell a story of practical challenges and ingenious solutions. They speak of the immense physical effort required, but also of the clever adaptations that made the impossible seem routine. What can these subtle variations teach us about the people who made them? The answer lies not in the marks themselves, but in the forgotten technology they point toward. These medieval building sites were a whirlwind of coordinated effort. Think of a great cathedral rising not in silence, but amid the constant noise of hundreds of workers. Masons shaped blocks with iron chisels, carpenters erected massive wooden frameworks, and laborers hauled stone from distant quarries using little more than ropes, sledges, and raw muscle. Historical accounts from monastic chronicles tell us who commissioned these wonders and how long they took to build, but they are strangely silent on the precise methods used to achieve such staggering precision. The written records celebrate the faith and the patrons, but they leave out the engineering. This gap in our knowledge is where the tool marks become so vital. They are the unwritten manuals, the lost instructions for achieving the impossible. What fueled this immense activity was a powerful mix of faith, ambition, and economics. The great Gothic building boom was not just about reaching heaven, it was about displaying power and consolidating community. Kings and bishops competed to erect the most awe-inspiring structures, pouring vast resources into projects that could take generations to complete. This demand created a highly organized society of builders. The Mason guilds protected their trade secrets fiercely, passing down techniques from master to apprentice in a closed oral tradition. This system ensured high quality, but it also meant that specialized knowledge could vanish overnight if a guild dissolved or a master craftsman passed away without a full successor. Consider the logistics alone. The specific limestone for a cathedral might be sourced from a quarry 50 miles away, chosen for its color and durability. Transporting these multi-ton blocks required a sophisticated network of barges, carts, and roads, a feat of organization that rivals any modern project. This context forces us to ask a critical question. How could builders working with what we see as rudimentary tools achieve such consistency and scale? The environmental and cultural pressures were immense. They had to work with the materials at hand, often under tight schedules and with limited budgets. This pressure to adapt, to innovate with what was available, is the crucible in which forgotten technologies were forged. The tool marks we find are not just scratches, they are the physical evidence of that relentless, creative problem-solving under pressure. That popular image of the medieval builder is a man swinging a crude hammer, creating rough, uneven stonework. This assumption of primitive tools producing crude results is perhaps our biggest blind spot. We look at the sheer scale of a cathedral and assume it must have been built with brute force and simple iron, yet the physical evidence tells a completely different story. This stereotype is reinforced by films and books that depict the era as universally rustic, ignoring the quiet sophistication preserved in the stone itself. The historian Professor Ian McCullough points out that early academics often dismissed these subtle tool marks as unimportant, mere byproducts of labor rather than critical data points. They were looking for grand narratives of kings and battles, not the microscopic signatures of a drill bit. This dismissal created a foundational myth of technological simplicity that we are only now beginning to correct. Consider the deep, perfectly cylindrical holes found in the foundations of some Saxon churches. A simple hand-powered drill with a basic metal bit simply could not achieve such uniformity and depth in hard granite. The mark itself is a silent protest against our assumptions, pointing to the use of a specialized, stable tool, perhaps one with a weighted mechanism or a complex bearing system that has been completely lost to time. When we insist on seeing only hammers and chisels, we are not seeing the past clearly. We are seeing a reflection of our own underestimation. The persistence of these simplifications costs us a true understanding of human ingenuity. It creates a false divide between a supposedly simple past and our complex present. But the stones insist there was no such divide. The builders possessed a sophisticated toolkit, both physical and intellectual, that we are only beginning to decode. By letting go of the myth of the primitive craftsman, we open a door to a much more fascinating truth, one where innovation was not just possible but absolutely necessary. The marble altar of a French abbey holds a silent challenge to our historical timeline. Its surface is marked by long, impossibly straight cuts, incisions so precise they seem to have been made by a machine. There is no wavering, no telltale dip or curve that would betray the unsteady hand of a craftsman. This is not an isolated case. From the cloisters of Normandy to the great English cathedrals, these flawless lines appear in the most prestigious structures, a signature of a technology we have forgotten. Laser scans of these surfaces reveal a secret hidden to the naked eye. They show microscopic grooves running in perfect parallel, patterns that could only be left by a blade moving on a fixed, guided path. This is not the work of a freehand chisel. It suggests the use of a mechanical aid, a saw or cutting frame that held the tool in perfect alignment, stroke after stroke. Look at the intricate stone screens of Canterbury Cathedral, where complex geometric patterns are assembled from dozens of individually carved pieces. The edges of these stones fit together with a seamlessness that is difficult to achieve even with modern tools. The tool marks here align with a fascinating theory: the use of template-based cutting systems. Master masons likely created precise wooden or metal templates. A less skilled worker could then trace this pattern using a guided tool, ensuring every piece was identical. This was not mass production, but it was a systematic approach to achieving uniformity on a grand scale. So what kind of device could make such a cut? Experts studying these marks proposed tools that are nowhere to be found in medieval illustrations: lever-based mechanisms that provided mechanical advantage or rotational systems that turned muscle power into smooth, consistent motion. These were not power tools, but they were clever contraptions that amplified human skill, transforming a strenuous, erratic process into one of controlled, repeatable precision. The existence of these guided blades forces a profound reevaluation. It suggests that the medieval workshop contained a level of mechanical sophistication we never credited it with, a quiet industrial revolution whose blueprints were simply worn away by time. Deep within the granite blocks of a Norman keep, you find a second type of clue, one that speaks of relentless, perfect motion. These are the symmetrical drill holes, each one a near-perfect cylinder bored deep into unyielding stone. Their uniformity is startling. A worker using a simple hand drill, a tool spun back and forth between the palms, would leave a telltale mark, a slightly wobbly, irregular channel. But these holes are different. Their circular symmetry is so precise it suggests a tool held in perfect alignment, driven by a consistent rotational force that human hands alone could not sustain. These are not solitary marks either. They often appear in careful groups, a pattern of dots that once guided the splitting of massive stones. This arrangement is the key. It implies a tool that could be repositioned quickly and accurately, a device that allowed for both speed and perfect repetition. The question is not just what made the hole, but what held the tool so perfectly steady time after time. Monastic records from the period occasionally mention mysterious devices called piercing engines, listed in inventories of tools, but these written words are ghosts, names without blueprints. They hint at the existence of specialized apparatus, but their designs are left entirely to our speculation. To understand how these piercing engines might have worked, we look to the application of force. The consistent rotation points toward mechanisms that transformed simple, back-and-forth motion into smooth, continuous spinning. A bow-driven drill, much like a fire-starting tool but on a massive scale, is one strong possibility. Pulling the bow back and forth would spin a drill bit with far greater speed and stability than human palms could manage. For even larger projects, some researchers point to the potential for water-powered mechanisms, using the relentless flow of a stream to turn a drive shaft that operated multiple drills at once. This was not magic, it was mechanical advantage. The fascinating part is that this technology may not have been a new invention, but a rediscovery. Look at the drill marks left in Roman masonry created centuries earlier. The similarity is uncanny. This suggests a thread of technological continuity, a secret of stoneworking that was passed down, lost, and then independently reinvented by medieval engineers facing the same physical challenges. How did they maintain such consistency in granite and marble? The answer is written in the stone itself. They used tools that were not crude or simple, but specialized, stabilized, and designed to enhance human productivity to an incredible degree. This evidence of symmetrical holes shatters the image of the lone craftsman struggling with basic iron. It paints a new picture, one of organized workstations, of ingenious devices that turned brute effort into controlled, repeatable precision, giving builders the flexibility to execute complex designs that would otherwise have been impossible. The most intricate carvings on a Gothic facade whisper a secret of production, not just artistry. Look closely at the repeating floral motifs, the endless vines and leaves that wrap around a cathedral's doorway. At a glance, they appear to be the work of a master sculptor's freehand genius, but the tool marks tell a different story. In the soft limestone of Chartres, you can see tiny, precise grooves running along the center of every identical petal and leaf. These are not the varied strokes of an artist interpreting a design. They are the ghostly impressions of a guide, a physical template that ensured every single element was reproduced with exacting sameness. This was not a limitation of creativity, but a triumph of engineering for mass production. How do you decorate a building the size of a city block with millions of intricate details? You develop a system. Guild records from the period occasionally mention the use of pattern books, collections of designs that were circulated among workshops. But the books themselves have largely crumbled to dust, and the crucial step, the method of transferring a small drawing onto a massive block of stone, remains one of history's great silent gaps. The evidence, however, is still etched in place. The consistent depth and angle of these carving marks point to the use of specialized instruments. A large compass or a series of them could have scribed the perfect circles for halos and rose windows. But for more complex, scalable patterns, researchers see the potential for early pantograph systems. This is a device that uses a system of linked arms to trace a small design and simultaneously reproduce it at a larger scale on a different surface. A master could create a perfect, small-scale model in clay or wood. An apprentice could then use the pantograph to trace it, with the machine guiding his chisel to replicate the design perfectly on the waiting stone. This explains the incredible uniformity. The tool marks are not erratic. They follow a consistent path and depth because the human hand was being assisted, its potential for error minimized by a mechanical guide. This changes the entire picture of the medieval workshop. It was not a chaotic atelier of individual geniuses, but a highly organized production line. One team quarried the stone, another rough-shaped it, and another, using these template systems, carved the intricate details that gave the building its soul. The sheer ambition of these projects demanded this kind of replicable process. It allowed for the work to be distributed among many hands without sacrificing the coherence of the final vision. The stones themselves ask us a compelling question. Could any of us, even with modern training, reliably carve 100 identical leaves by hand? The difficulty of that task underscores the brilliance of their solution. They did not just build with stone, they developed the very systems that made such grandeur possible, leaving behind not just a beautiful facade, but the subtle, machined marks of a forgotten industrial process. The stone blocks of a medieval bridge fit together so perfectly that not even a blade of grass can slip between them. This seamless join is no accident. It is the final result of a hidden process, one revealed by the uniform grooves carved into the mating surfaces of the stone. These are not rough scratches. They are systematic, often V-shaped or gently curved channels, precisely cut to increase the surface area for mortar and to lock the stones in place against immense pressure. The consistency of these grooves across thousands of blocks tells a clear story. They were not made by freehand chiseling. The unwavering lines point to the use of guided tools or simple jigs, wooden or metal frames that held a chisel at a fixed angle, allowing a worker to produce the exact same cut over and over again. Modern engineering studies have put this ancient wisdom to the test. Stress tests on scale models demonstrate that these interlocking joints dramatically improve a structure's ability to distribute weight and resist shifting. This was not just decorative craftsmanship, it was advanced structural engineering encoded in stone. We see this same principle in the enduring aqueducts and formidable fortification walls. The tool marks left on their stones align perfectly, suggesting that teams of masons used template-based dressing tools. A master would set the pattern, and the entire team could then replicate it, ensuring that every block, no matter who shaped it, would fit with its neighbor. This approach had profound practical benefits. It drastically reduced waste as stones were cut correctly the first time. It also sped up construction to an incredible degree, functioning almost like a modular building system centuries before the term was invented. How did they maintain such flawless consistency from one end of a vast project to the other? The answer lies in the standardization of the process, not just the material. By creating simple, reusable guides for these crucial joints, medieval builders achieved a level of efficiency and durability that we are only now fully appreciating. The quiet evidence of these uniform grooves challenges one of our most basic assumptions, that such precision requires complex machinery. It suggests instead that their greatest invention may have been a system of thought, a method for turning individual skill into collective, repeatable perfection. The final, lustrous polish on a medieval tomb effigy holds a secret in its reflection. These surfaces are not merely smooth, they possess a deep, uniform sheen that seems to swallow the light, a finish that goes far beyond what simple hand sanding with a rough stone could ever achieve. On the marble effigies in places like Westminster Abbey, this is not a feature of age but of original intent. Under microscopic examination, the story becomes clear. The surface is covered in thousands of tiny, parallel scratches, all flowing in the same consistent direction. This pattern is the unmistakable signature of a rotary tool, a wheel spinning at high speed with an abrasive paste, systematically and mechanically wearing the stone down to a perfect, reflective plane. Manual polishing, by its very nature, creates chaotic, cross-hatched striations as the hand moves in unpredictable, circular motions. The order found here speaks of a machine's relentless, single-minded motion. Historical workshop inventories sometimes list mysterious devices called lapping engines, a name that evokes a complex apparatus, yet their designs have been lost. We are left with only the ghost of their function preserved in the stone itself. So what could such a device have looked like? It might have employed a simple foot treadle, much like a spinning wheel, to rotate a flexible shaft. This shaft could have held a range of polishing heads, from stiff discs for initial shaping to soft leather wheels charged with fine abrasive powders for the final, mirror-like finish. The use of different abrasives, from crushed quartz to increasingly fine emery, would explain the progressive stages of smoothness, each grade removing the scratches of the one before it. This was not a crude process. It was a sophisticated, multi-step finishing technique that required a stable power source and a precise understanding of material science. The presence of these polished surfaces on curved, complex shapes, like the folds of a stone robe or the intricate details of a knight's armor, points to an even more fascinating possibility. For such three-dimensional work, a simple rotating wheel would not suffice. This suggests the use of small, handheld rotary tools, perhaps even early ancestors of the flexible shaft, allowing an artisan to reach into crevices and follow contours with controlled, mechanical precision. The pursuit of this perfection was not purely aesthetic. A highly polished surface is far more resistant to the elements, shedding water and resisting the accumulation of grime that weathers rough stone. This combination of breathtaking beauty and profound practicality is the hallmark of these forgotten technologies. They were not secret arts but efficient solutions. The evidence of these anomalous abrasion marks compels us to reconsider the very air of a medieval workshop. It was likely filled not only with the sound of hammer blows, but with the persistent, whirring hum of spinning wheels, transforming rough stone into luminous surfaces that have captured the light for centuries. The floors of great medieval halls hold a secret beneath our feet. Look down at the vast stone slabs, and you will see them, thousands of parallel lines scored into the surface with a rhythm that feels almost mechanical. These are not the random scratches of daily wear. They are deliberate, evenly spaced grooves, a repetitive pattern that stretches from one end of the room to the other, too uniform to be the work of a single mason working freehand. This is the sixth piece of evidence, a subtle yet powerful testament to a system of organized construction. At first glance, you might think they are merely decorative, but their true purpose was profoundly practical. In the damp climates of Northern Europe, these grooves provided essential traction, a built-in non-slip surface for stone floors that would otherwise become treacherous when wet. Yet their function did not stop there. Archaeologists excavating civic buildings and merchant guild halls have found identical scoring on the underlying foundation layers, surfaces that would never be seen. Here, the lines acted as a guide, a literal grid for the perfect alignment of the finished floor slabs above, ensuring every tile was laid straight and true. How could such perfect repetition be achieved? The answer lies in the tool itself. Three-dimensional imaging of these scores reveals microscopic variations in the groove edges, patterns that suggest a single tool with multiple cutting edges was used, perhaps a blade holder with several fixed points. This would allow a worker to carve 5 or 10 perfect lines with a single pass, transforming a laborious task into one of swift, efficient execution. In the stone records of Italian palazzos, these marks align with brief written accounts of lineation devices, tools used by masons to inscribe guiding patterns directly onto stone. Why was this so widespread? The prevalence of these scores speaks to a driving need for workflow efficiency on a massive scale. They represent a move away from unique, one-off solutions toward standardized, repeatable processes. This was not about artistic expression, but about building smarter. It reveals a mindset that valued precision in the most mundane tasks, understanding that the integrity of the entire structure depended on the perfection of its most hidden details. What does this tell us about the medieval builder? He was not just a craftsman, but a systems thinker, using clever, multi-purpose tools to conquer the immense challenge of scale, one perfectly parallel line at a time. A stone block in a forgotten quarry corner holds a set of faint, precise lines and a carved Roman numeral 7. This is not graffiti. It is a technical drawing, a set of instructions left directly on the raw material by a builder who saw the finished cathedral in his mind's eye. These incised measurement markings are the seventh piece of evidence, a blueprint etched in stone that reveals a hidden world of calibrated tools and sophisticated planning. We find them in the foundations of English castles and the hidden surfaces of cathedral walls, placed there to guide the assembly of thousands of individual blocks into a single, coherent whole. The angles and lengths are not approximate. They are exact, implying the use of highly accurate rules and protractors to inscribe them. Historians can point to a few surviving brass measuring rods and beautifully crafted metal protractors from the period, precious objects that confirm the knowledge of precise measurement existed. But this raises a deeper puzzle. How did they transfer these perfect measurements onto massive, irregular blocks of stone at a quarry, miles away from the building site? The tools for this scribing process at an industrial scale are the true mystery. The marks themselves provide the clues. Look at the clean, sharp V-shape of the incised lines. A simple metal stylus dragged by hand would create a wandering, uneven groove. The consistency of these marks suggests the use of a guided scribe, a tool that held a sharp point at a fixed distance from a straight edge, perhaps even a primitive but effective form of the caliper. This allowed a worker to replicate a standard unit of measurement, like a foot or a palm, with perfect repetition across an entire consignment of stone. In castles like Dover, the markings on the stones align perfectly with the complex geometries found in surviving architectural plans, the large drawings on parchment that guided the entire project. This connection is vital. It tells us that the design was not just an idea, it was a set of data that could be communicated and executed with machine-like accuracy by a dispersed workforce. The master mason at the cathedral site could send a detailed template, a set of numbered and coded instructions, to the quarry miles away. The quarry workers, using their calibrated scribing tools, would then carve those instructions directly onto the blocks. When the stones arrived at the building site, they were not just a pile of rock. They were a pre-fabricated kit, each piece numbered and marked for its specific location in the grand design. This system of incised communication bears a striking parallel to modern surveying and metrology. It is a physical language of construction, a code that ensured every component, shaped by different hands in different places, would fit together flawlessly. How did they maintain this accuracy across such vast distances and over decades of work? The answer is in the system itself, a system of precise, replicable measurement that turned grand architectural visions into immutable stone reality, one perfectly inscribed line at a time. A stone block in a forgotten quarry corner holds a set of faint, precise lines and a carved Roman numeral 7. This is not graffiti. It is a technical drawing, a set of instructions left directly on the raw material by a builder who saw the finished cathedral in his mind's eye. These incised measurement markings are the seventh piece of evidence, a blueprint etched in stone that reveals a hidden world of calibrated tools and sophisticated planning. We find them in the foundations of English castles and the hidden surfaces of cathedral walls, placed there to guide the assembly of thousands of individual blocks into a single, coherent whole. The angles and lengths are not approximate. They are exact, implying the use of highly accurate rules and protractors to inscribe them. Historians can point to a few surviving brass measuring rods and beautifully crafted metal protractors from the period, precious objects that confirm the knowledge of precise measurement existed. But this raises a deeper puzzle. How did they transfer these perfect measurements onto massive, irregular blocks of stone at a quarry miles away from the building site? The tools for this scribing process at an industrial scale are the true mystery. The marks themselves provide the clues. Look at the clean, sharp V-shape of the incised lines. A simple metal stylus dragged by hand would create a wandering, uneven groove. The consistency of these marks suggests the use of a guided scribe, a tool that held a sharp point at a fixed distance from a straight edge, perhaps even a primitive but effective form of the caliper. This allowed a worker to replicate a standard unit of measurement, like a foot or a palm, with perfect repetition across an entire consignment of stone. In castles like Dover, the markings on the stones align perfectly with the complex geometries found in surviving architectural plans, the large drawings on parchment that guided the entire project. This connection is vital. It tells us that the design was not just an idea, it was a set of data that could be communicated and executed with machine-like accuracy by a dispersed workforce. The master mason at the cathedral site could send a detailed template, a set of numbered and coded instructions, to the quarry miles away. The quarry workers, using their calibrated scribing tools, would then carve those instructions directly onto the blocks. When the stones arrived at the building site, they were not just a pile of rock. They were a pre-fabricated kit, each piece numbered and marked for its specific location in the grand design. This system of incised communication bears a striking parallel to modern surveying and metrology. It is a physical language of construction, a code that ensured every component, shaped by different hands in different places, would fit together flawlessly. How did they maintain this accuracy across such vast distances and over decades of work? The answer is in the system itself, a system of precise, replicable measurement that turned grand architectural visions into immutable stone reality, one perfectly inscribed line at a time. The edge of a medieval chisel recovered from a monastery workshop tells its own story of specialization. Its wear is not uniform, but concentrated on one specific corner, its metal hardened through a unique tempering process to withstand the abrasive grit of granite. This is not a general-purpose tool. It is an implement engineered for a single, brutal task. Archaeologists call this the eighth evidence, a world of specialized tools revealed not just by the objects themselves, but by the unique signatures they left on the stone. In German monastic ruins, the tool marks on a soft limestone wall are broad and shallow, left by a wide, forgiving blade meant for rapid shaping. Just a few feet away, on a granite foundation block, the marks are entirely different, short, deep, and percussive, made by a narrow, heavily reinforced chisel designed to fracture the hard stone without shattering itself. This is not a matter of using the same tool for different jobs. It is the clear footprint of a tailored toolkit. Metallurgical analysis of surviving tool hoards confirms this sophisticated approach. Artisans did not just have chisels, they had chisels of varying carbon content and temper, each alloy carefully selected to match the material it was meant to conquer. A soft iron chisel would be ruined on granite, while a super-hardened steel one might be too brittle for fine marble work. They possessed a practical, working knowledge of material science, understanding that different stones demanded different edges, different angles, and different levels of force. This specialization speaks to a highly developed division of labor. An apprentice might begin his career learning to rough out blocks with heavy hammers and pitching tools. A journeyman would graduate to the precise chisels for detailed carving. The master overseeing the work would have possessed the specialized, often custom-made implements for the most critical tasks, like undercutting or creating the final decorative flourishes. What do these wear patterns teach us about skill development? They reveal a career path carved in metal and stone. A worker's progression was marked by his access to and mastery over an increasingly sophisticated set of tools. This was not a random collection of iron. It was a nuanced tool economy, where the right implement was deployed for the right job to maximize both efficiency and quality. The stones bear witness to this hierarchy of skill, each distinct wear pattern a testament to a craftsman who knew his material so intimately that he used a tool created for that material alone. High above, in the shadowed vaults of a Spanish cathedral, the stone is punctuated by a grid of perfect little holes. Each one is a clean, dark circle, bored straight into the ceiling as if by a giant, precise insect. These are not the rough, irregular pits left by a punch and hammer. Their edges are sharp and defined, with almost no chipping or fracture lines around the rim. This ninth piece of evidence, these unusual perforations, points to a tool that could bite into stone with controlled, relentless force. We find them in chapter houses and crypts, often arranged in deliberate geometric patterns, a secret code of dots on the ceiling. Their placement is too systematic to be accidental. Engineering analysis of these spaces reveals a fascinating possibility. The patterns often align with areas where sound would gather or where structural stresses were highest. This suggests they may have served a dual purpose, perhaps as part of a sophisticated acoustic system to dampen echoes in a reverberant space, or as clever anchor points for a since-vanished framework. The mystery is not their function but their creation. How do you create 100 identical holes, each a perfect cylinder, high overhead on a curved stone surface? The marks themselves hold the answer. The near-total absence of chipping around the edges is the critical clue. It tells us the tool that made them was not struck. It was turned with immense stability and constant pressure. A simple handheld drill would have wobbled, especially when working overhead, leaving a telltale trail of broken stone around the opening. The cleanliness of these perforations implies a tool that was firmly braced, a core drill or auger that was mechanically stabilized. Historical craft manuscripts from the period sometimes make fleeting reference to specialized piercing tools used by stonemasons. But these are just names in a list, ghost terms like stone bores or vault augers, with no drawings or descriptions to bring them to life. We are left to reconstruct their form from their function. The technology likely did not emerge from a vacuum. It was almost certainly adapted from other trades. Consider the shipwright's auger, a massive tool used to bore through heavy timbers, or the cooper's drill for making barrels. These were tools designed for precision in tough materials. It is a small leap to imagine a mason seeing such a device and realizing its potential, adapting its design to bite into stone instead of wood. The secret may have been in the bit itself, a tip hardened and shaped to grind its way through rock, perhaps using sand and water as an abrasive, all while being turned by a powerful, geared mechanism that provided both downward force and smooth rotation. These perforations are more than just holes. They are the imprint of a borrowed idea, a testament to the cross-pollination of technologies in the medieval world. They show us that builders were not isolated in their workshops. They were observers, innovators, who looked at the tools of other crafts and asked a simple, revolutionary question. What if we used that on stone? A spiral column in a French cloister seems to writhe with life, its stone surface carved into perfect, undulating grooves that spiral from base to capital. Running your hand along its length, you feel a rhythm so consistent it could only be the work of a machine. These are not the hesitant, wobbly lines of a chisel guided by hand. They are the 10th and perhaps most dramatic evidence, the unmistakable signature of a rotary lathe used to turn solid stone. We find these spirals on decorative columns, ornate balusters, and intricate baptismal fonts across Europe, all sharing that impossible symmetry. The tool marks here are continuous and uniform, following a perfect helical path that a sculptor working freehand could never hope to replicate over such a distance. The stone itself appears to have been spinning while a stationary cutting tool was pressed against it, shaving away everything that did not belong to the final, elegant form. Surviving manuscripts from monastic libraries contain tantalizing clues, small marginal illustrations of crank handles and pole lathes used by woodworkers. While no full-scale stone-turning lathe has been preserved, the principle is clear in these drawings. A heavy stone block could have been mounted on a central axle. A large wheel, perhaps driven by a foot treadle or even flowing water, would then spin the mass, bringing the entire form to life under the steady hand of a craftsman guiding the cutting tip. This was not just a tool, it was a transformative apparatus. It allowed for the mass production of complex, identical decorative elements. Think of a great chapel requiring dozens of identical spiral columns. With a lathe, a workshop could produce them all to the same exact specification, ensuring visual harmony and dramatically speeding up the embellishment of the building. What enabled the adoption of these mechanical helpers? It was a convergence of necessity and available technology. The same gear and crank systems understood by millwrights for grinding grain could be repurposed. The same principles of rotational force used by potters could be scaled up. This evidence completely shatters the view of medieval construction as an entirely manual, muscle-driven process. It points instead to a quiet, widespread early industrialization, where human skill was amplified by clever machines to achieve a level of ornamental precision that still takes our breath away. High on the weathered walls of the Tower of London, a massive block of limestone bears a series of curious, worn notches along its bottom edge. These are not decorative carvings or accidental damage. They are the 11th and perhaps most physically telling piece of evidence, the subtle scars left by the immense effort of lifting multi-ton stones into the sky. These specific grooves and polished channels align perfectly with the points where levers were inserted or where ropes and chains made contact, guiding us toward the sophisticated lifting gear that made medieval skylines possible. When you trace the pattern of these marks across a wall, a system emerges. They often appear in sets of 2 or 3, spaced at regular intervals, creating a clear map of the contact points for a lifting apparatus. Paired with these notches are other, subtler abrasions, the ghostly polish left by thick ropes sliding under tremendous tension, or the distinctive scoring from metal chains. This combination tells a complete story, not of brute force, but of controlled mechanical advantage. Period building contracts and monastic chronicles do mention these devices, referring to them with the wonderfully vague term engines for raising stone. But the written word gives us no blueprints. It is the stone itself that holds the true design specifications. By carefully mapping these tool marks at sites like the tower and comparing them to known physics, engineers can reverse engineer the likely mechanisms. The patterns point toward the use of cranes far more complex than a simple pulley on a tripod. The consistent spacing and depth of the lever notches, for instance, suggest a revolving platform at the crane's head, a device that could swing a heavy block safely into its precise position without having to lower and re-rig it. How did they power such a machine? The evidence points to massive tread wheels, those great wooden wheels you sometimes see reconstructed in cathedral towers, powered by men walking endlessly inside them. This was not just manpower, it was human power harnessed and magnified by a gear system, transforming the slow, steady pace of a walk into the immense, controlled torque needed to lift a block weighing as much as 2 elephants. Other marks, particularly those found on fortress walls in remote locations, hint at the use of animal power, with donkeys or oxen driving a capstan, a rotating drum that wound in the heavy lifting ropes. The true ingenuity lies in the safety mechanisms these wear patterns imply. The precise positioning of the notches reveals an understanding of a stone's center of gravity, ensuring it could be lifted without tipping or slipping. The rope abrasions show a system that could hold a load securely and lower it with just as much control as it was raised. This was technology built for reliability, for handling immense weights day after day, year after year, with a margin of safety that protected both the priceless stone and the workers below. These forgotten impressions are the direct physical proof of a silent partnership between human intention and mechanical invention, a partnership that quite literally raised the foundations of the modern world. The serene face of a marble saint in an Italian altarpiece is a testament to efficiency. Its features are sharp and defined, yet the surface around them has a soft, almost liquid sheen. This is not the result of 2 separate tools, one for carving and another for polishing. A microscopic look reveals a single, continuous transition from the deep cut of an eye socket to the gentle curve of a polished cheek. This 12th evidence, the hybrid mark, points to a tool that could both cut and finish, an implement of adaptable purpose. We find these composite effects on the complex surfaces of public fountains and intricate choir stalls, where the stonework shows a seamless flow from aggressive shaping to final refinement. The tool mark itself is a fusion, a groove that begins with the rough texture of a cut and ends with the fine striations of a polish, all in one uninterrupted pass. This is the signature of a composite tool, a device with interchangeable heads or a multi-function design. Archaeological digs near old workshop sites have unearthed tantalizing fragments, metal shanks with clever socket systems designed to hold different bits. A single handle could accept a drill head for boring a hole, a carving chisel for defining detail, and a polishing pad for achieving the final luster, all without the craftsman ever setting down his primary tool. Why would this matter on a sprawling project? The advantages were profound. It saved immense time, eliminating the constant switching between heavy, specialized implements. It conserved precious metal, as one robust handle could serve a dozen purposes. Most importantly, it allowed for a continuous creative workflow. An artisan could rough out a form, refine its details, and begin the smoothing process in a fluid sequence, maintaining his artistic momentum and his precise grip on the work. This innovation did not emerge from the stonemason's yard alone. The design of these modular fittings bears the unmistakable influence of metalworkers, masters of precision who created complex tools for engraving and filing. This cross-cultural exchange was vital. The metalworker understood alloys and fine mechanisms, while the mason understood stone and immense pressure. Their collaboration produced a new class of implement, one that brought the finesse of the jewelry workshop to the scale of cathedral construction. These hybrid marks are more than just evidence of a clever device. They represent a fundamental shift in thinking, a move away from a collection of single-use tools and toward an integrated, versatile system. It was a pragmatic solution for an era of grand ambitions, where the only limit was the ingenuity of the human hand and the adaptable technology that extended its reach. The faintest shadows on a stone surface can reveal the deepest secrets of the workshop. In the soft morning light of a Burgundy chapel, conservationists use raking light photography, shining a beam at an extreme angle to reveal what the naked eye cannot see. What emerges are not carvings but ghosts, the subtle outlines of long-vanished wooden or metal frames that were once clamped directly to the stone. These are the 13th evidence, the subtle impressions left by temporary guides and jigs. The tool marks tell a clear story. Inside these faint borders, the chisel work is confident and precise, but outside these lines, the strokes are more tentative. This is the footprint of a system designed for mass production and consistent quality. The guide acted as a physical boundary, a trainer for the hand, ensuring that every cut, even one made by a less experienced apprentice, stayed within the strict limits of the design. This was particularly vital for the most repetitive elements, like the intricate stone tracery of a rose window, which required dozens of identical, curving pieces. A master could carve a single, perfect template. That template could then be used to create a durable jig, a reusable frame that allowed an entire team of workers to produce components that were interchangeable. Historical guild records sometimes cryptically mention these pattern frames in lists of approved workshop equipment, but the objects themselves, being temporary, have almost entirely returned to dust. Their existence is inferred entirely from the negative space they left behind. The pristine stone protected under the frame contrasted with the worked surface around it. How did these simple guides shape the efficiency of a medieval worksite? They were the great democratizers of skill. They broke down a master's complex vision into a series of simple, repeatable tasks. This system allowed a large, mixed-ability workforce to contribute to a grand project without compromising the flawless unity of the final result. It was a form of early quality control, a physical assurance that every piece would fit. The true innovation was not in the chisel that cut the stone, but in the wooden frame that guided the hand holding the chisel. This shift from relying solely on individual genius to creating systems that enabled collective perfection is a quiet revolution. It suggests that the most powerful tool in the medieval workshop may not have been made of iron at all, but of oak and a simple, brilliant idea. The very stone itself guided the craftsman's hand. Deep within a granite block from a medieval quarry, a petrographic microscope reveals a hidden history, not of the rock but of the tool that struck it. The microscopic fractures radiating from a chisel mark are not random. Their specific pattern, a delicate web of cracks, indicates the precise hardness and angle of the tool's edge, a cutting face engineered to match the stone's unique behavior under stress. This is the 14th evidence, a silent conversation between material and tool, written in microscopic script. Geologists studying these marks can now distinguish between tools used on the soft limestone of France and the hard basalt of German castles. The chisel marks on a brittle marble, like that used for the cladding of Siena's cathedral, are shallow and controlled, designed to flake the material away without shattering the entire slab. Just a few miles away, on a site using a more ductile sandstone, the marks are deeper and more aggressive, made by a tool that could gouge and peel the tougher stone. This was not guesswork, it was an applied science, a practical understanding of physics and geology, refined through generations of hands-on experience. The builders possessed an empirical knowledge of material science, selecting and even forging their tools based on the specific quarry they were working. A chisel used on soft chalk would have a different temper, a different cutting angle than its cousin destined for hard granite. This deep material awareness had profound practical benefits. It minimized wasted stone, as blocks were less likely to fracture during shaping. It drastically reduced the physical effort required, making the impossible task of shaping a mountain into a cathedral just slightly more manageable. Why does this matter? It reveals that innovation was not just about creating new machines, but about perfecting the intimate relationship between the tool and its target. The medieval artisan did not see a block of stone. He saw a material with specific properties, and he reached for a tool that was quite literally made for the job. A partnership of human intellect and earthly material that has left its flawless signature for us to find. A Roman aqueduct and a medieval castle stand as monuments from different worlds, yet their stones share a common language. Place a cast of a drill hole from a Roman foundation next to one from a Norman keep. At first glance, they are nearly identical, both displaying that telltale cylindrical symmetry that speaks of a stabilized, rotating tool. This parallel suggests not a dark age of forgetting, but a thin, unbroken thread of technical knowledge, passed from one generation of builders to the next, perhaps through the quiet continuity of monastic workshops that preserved practical arts. Yet look closer, and the story becomes more complex. On the harder, more stubborn granites preferred for medieval fortifications, the chisel marks are often deeper and more aggressive than those found on Roman marble. This is not a regression, it is an adaptation. The medieval mason was not working with the relatively soft, uniform stones of the Mediterranean. He was conquering the erratic, flint-filled limestones and brutal granites of the north, and his tools evolved to meet that tougher challenge. Historians carefully study these divergences, debating whether the changes represent a loss of sophisticated Roman engineering or a purposeful evolution driven by new materials and new ambitions. A cathedral was not an aqueduct, It required different techniques for different forms. We see this dialogue between eras literally set in stone through the reuse of Roman materials, known as spolia. In the walls of countless medieval churches, you can find a Roman column or a carved lintel from a ruined villa, its original smooth surface now punctuated by fresh, deeper chisel marks where the medieval mason recut it to fit his new design. The old tool marks were not sacred, they were just material to be reworked. This practice tells us that while the medieval builder respected the quality of Roman stone, he was not bound by their methods. He applied his own technology, his own understanding to the ancient block. Why did the precise stone-cutting saws of the Romans, which left such glassy surfaces, seem to fade from use? The answer may lie in the economics of the time. The large, stable industrial quarries that supplied the Roman Empire collapsed. The medieval mason often worked with smaller, local quarries where the scale of operation no longer justified the immense, water-powered sawmills of antiquity. His toolkit became more versatile, more adaptable to changing sites and resources. This comparative view across centuries reveals that technology is not a straight line ascending ever upward. It is a river with currents that slow, split, and sometimes merge again. The story of these tools is not one of simple progress or loss, but of a constant, intelligent conversation between the needs of society and the materials of the earth. The sealed doors of a medieval mason's guild held more than just men. They safeguarded the very tools that shaped an era. Inside these workshops, innovation was a currency more valuable than gold, a closely guarded secret that gave one group of builders a critical edge over another. This 16th evidence is not found in a single mark, but in the startling consistency of thousands. When you see the same distinct, short chisel score repeated on buildings across a region, you are not looking at one craftsman's signature, you are seeing the trademark of an entire organization. The guilds, as detailed in their own surviving charters and ordinances, were not just labor unions, they were the research and development centers of their day, fiercely regulating everything from the quality of iron in a chisel to the 7-year journey of an apprentice. Their primary goal was to maintain a monopoly on skill, and that meant controlling the technology. The written records they left are frustratingly vague on specifics, often speaking in broad terms about tool standards, because the precise methods were considered proprietary knowledge, passed down orally from master to apprentice in a closed, secure chain. This secrecy is precisely why the tool marks are so vital. They are the unguarded testimony of these protocols. Consider the ordinances of the Strasbourg Masons, which meticulously outline the maintenance of tools and the stages of apprenticeship. A journeyman was not permitted to use the fine finishing chisels reserved for a master. This hierarchy of access is physically recorded in the stone. On a single pillar, you might find the deep, rough gouges from a junior worker's standard tool, and right beside it, the shallow, incredibly precise incisions from a master's specialized, razor-sharp chisel. The guild did not just teach men how to carve, it dictated which tool to use for every single cut, creating a system of production so standardized that the mark of the organization became more distinctive than the mark of the individual. What role did this intense specialization play in technological advancement? It created a pressure cooker for refinement. When a guild's reputation and income depended on producing superior work faster than its rivals, there was immense pressure to improve the tools of the trade. A master might experiment with a new alloy for a drill bit, or tweak the angle of a chisel's edge to make it more efficient on a particular type of local stone. A successful innovation would then become guild property, taught to all members as the new standard, and its distinctive signature would spread across the landscape. The consistent patterns we find, the uniform drill holes and the repetitive saw scores, are the direct result of this organized, collective push for perfection. The guilds did not just build cathedrals, they built the very toolkit that made cathedrals possible, leaving behind a legacy of technological excellence written in a language of stone and steel. A storm lashes the parapets of a Scottish sea castle for centuries, and the stone itself begins to record the battle against the elements. The tool marks on these coastal fortifications are not static relics, they are dynamic documents of environmental interaction. Where the salt-laden air constantly gnawed at the iron tools, the chisel marks left behind tell a dual story, one of the craftsman's intent and the environment's relentless response. In these exposed locations, the typical sharp-edged chisel score is often softened, its crisp lines blurred by a specific type of pitting and erosion that mirrors the corrosion pattern of the tool that made it. This is the 17th evidence where the very weathering of the mark becomes a clue. Through detailed corrosion analysis, researchers can look at this unique erosion signature and deduce the composition of the long-vanished tool. On one granite block, the marks might be deeply degraded, suggesting a standard iron tool that rusted quickly, requiring frequent sharpening or replacement that altered its cutting profile over time. Just a few feet away on the same wall, another set of marks remains surprisingly crisp and well-defined despite centuries of salt spray. This durability points to the use of a superior iron alloy, a metal intentionally crafted with a resistance to rust. Such a finding is profound. It suggests that builders working on these harsh coastlines possessed and applied a specific metallurgical knowledge, selecting or even formulating tougher tools for the most punishing environments. By carefully correlating the preservation state of thousands of these marks with historical climate data, a broader picture of workshop logistics emerges. The patterns can reveal maintenance cycles, showing how often tools were serviced or replaced based on the seasonal intensity of the weather. A cluster of sharply defined marks from a durable alloy might indicate a period of proactive preparation, perhaps before a stormy season, while a sequence of progressively degraded marks could tell a tale of a busy work period where tools were used until they literally wore away. How did these surroundings ultimately shape technological choices? The evidence from the sea castles suggests that the environment was a direct participant in the innovation process. It forced a problem-solving mindset that considered not just how to shape the stone, but how to preserve the means to shape it. The legacy of their tools is therefore written in two languages, the immediate language of the cut and the long, slow language of the wind and the sea, together adding a crucial layer of ecological context to our reassessment of their forgotten craft. The delicate stone tracery of a cathedral's rose window tells a story written in a different language than the rugged blocks of a town's defensive wall. One bears the intricate, almost microscopic marks of fine chisels and polishing tools, a testament to artistry and devotion. The other shows the deep, efficient grooves of heavy picks and robust saws, speaking of pure, unadorned function. This 18th piece of evidence reveals how the very purpose of a building directly dictated the tools used to create it, offering a stark contrast between the sacred and the secular in the medieval world. Look at the stone screens inside a great monastic church, where the tool marks are so fine they seem to disappear into the curves of the carving. These surfaces required specialized, razor-sharp implements and the steady hand of a master craftsman, a person whose skill was considered a form of divine service. Historical payroll records from these projects list higher wages for these specialized artisans, confirming that the finest work commanded the highest value, attracting talent from across the continent. Now compare that to the stonework of a busy market hall or a guild building. The marks here are broader, deeper, and more repetitive, the product of tools designed for speed and endurance. The primary goal was not to inspire awe through beauty, but to enclose a space quickly and durably for commerce and community gatherings. This difference in mark density and type is not a matter of quality, but of intent. A fortified gatehouse needed to withstand siege engines, not to display intricate foliage. Its tool marks are the signatures of brute strength and practical engineering. What do these divergent toolkits say about the society that wielded them? They reflect a clear hierarchy of values, where immense resources and the pinnacle of technological skill were lavished on structures meant to connect humanity with the divine. The church was a permanent spiritual investment, and its construction was an act of faith that justified any expense. The town wall, while equally vital, was a practical necessity, its construction governed by budgets, timelines, and the immediate need for security. This contrast enriches our understanding of medieval innovation, showing that technological expression was never blind. It was always guided by a powerful, invisible hand, the hand of human purpose. A modern chisel strikes a block of limestone, but this is not a construction site. It is a controlled experiment in a quarry, where a craftsperson using a replica of a medieval tool is trying to solve a 500-year-old puzzle. This is experimental archaeology, the 19th window into our past, where theory meets the unyielding reality of stone. Here, historical reenactors and researchers do not just study old marks, they create new ones, using tools forged from period-correct designs to see if they can replicate the precise signatures left on ancient walls. The goal is simple yet profound: to feel the same resistance, to hear the same sound, and to measure the exact force and time that defined a medieval workday. In one remarkable series of trials, craftsmen using a reconstructed bow drill, a tool with a cord wrapped around a shaft, were able to produce those mysteriously symmetrical bore holes in granite. The consistent back and forth motion of the bow generated a smooth, stable rotation that hand spinning alone could never achieve, and it required far less physical effort than previously assumed. These experiments reveal more than just technique. They unveil the rhythm of the workshop. How many strokes did it take to carve a single decorative leaf? How long to polish a square foot of marble? By timing these reconstructed tasks, researchers can begin to map out the true logistics of a project that spanned decades, transforming vague estimates into concrete, understandable timelines. The stones tell us what was done, but these reconstructions show us how it felt: the strain on the muscles, the focus required for each cut, and the quiet efficiency of a well-designed tool in a skilled hand. This hands-on approach bridges a vast gap, turning abstract hypotheses into tangible, physical truth. What we learn is that these forgotten technologies were not just effective, they were often elegantly efficient, born from a deep, practical wisdom that we are only now beginning to relearn by doing. A Venetian merchant's logbook from the 13th century lists not just silks and spices, but a cargo of specialized iron ingots destined for a cathedral workshop hundreds of miles inland. This was the bloodstream of medieval innovation, the vast network of trade routes that carried not only goods but the very seeds of technological change. The 20th evidence lies in the foreign fingerprints left on local stone, where tool marks reveal a silent, global conversation happening right under the noses of kings and bishops. Look at the intricate geometric patterns adorning a chapel in Norman Sicily. The patterns themselves are Islamic in origin, but it is the tool marks that tell the deeper story. The chisel work is not the broad, deep scoring of local masons. Instead, it is a series of incredibly fine, precise incisions, a technique perfected in the workshops of Cairo and Baghdad. This is not mere imitation, It is the direct application of a foreign technology, a new way of holding a chisel and understanding stone that arrived along with the spice caravans. Port cities like Venice and Genoa became living libraries of construction techniques. A stone block imported from Egypt might bear the distinct saw marks of a water-powered mill, a technology unknown in the north. When local masons worked this stone, they were not just shaping an imported material, they were reverse engineering the methods used to quarry and cut it, learning from the evidence left behind by a distant civilization. The trade in raw materials was just as critical. High-quality iron from Swedish mines or specialized abrasives like emery from Turkey traveled these routes, enabling toolmakers to forge harder, more durable chisels and drill bits. This access to superior materials directly translated into new possibilities, recorded in the cleaner, deeper, and more complex marks that begin to appear in the stonework of well-connected regions. Merchant guilds, the overlords of these routes, understood the immense value of this knowledge. Their records hint at strict controls, treating certain tools or techniques as proprietary secrets, as valuable as any luxury good. The movement of a master craftsman from one city to another could be a form of sanctioned technology transfer, or perhaps an act of industrial espionage with his specialized toolkit hidden among the bales of cloth. How did this connectivity foster a technological revolution? The marks on the stones are our answer. They show that innovation was rarely a solitary breakthrough in a secluded workshop. It was a collaborative, often accidental, process of cross-pollination. A new carving technique from Persia, a harder steel from Damascus, a new abrasive from North Africa. All these elements converged along the trade routes, merging with local traditions to create something entirely new. The next time you look at a Gothic cathedral, see it not just as a European achievement, but as a global project, its stones inscribed with the lost language of international exchange. The silent strength of a Gothic arch is a deliberate construction, not an accident of time. Look up at the soaring vault of a great cathedral and you will see the stones are not merely stacked, they are intricately keyed together. The surfaces where these massive blocks meet are not flat, they are carved with a series of precise, interlocking grooves and ridges, patterns left by chisels and saws that were used not just to shape but to engineer. These are the 21st evidence tool marks explicitly designed for structural integrity. Modern engineers use sophisticated computer modeling, a technique called finite element analysis, to simulate the forces flowing through these ancient structures. When they digitally reconstruct a cathedral arch without these keyed joints, the model shows dangerous stress concentrations at the weak points. But when they add the precise interlocking geometry revealed by the tool marks, the stress distributes evenly throughout the entire structure, transforming a potential point of failure into a source of collective strength. This is not guesswork, it is the physical proof of an empirical understanding of physics, a knowledge gained through generations of observation, failure, and success, encoded directly into the guild's standard operating procedures. The most dramatic examples are the flying buttresses, those stone arms that leap from the outside walls to brace the immense weight of the nave. The joints where these buttresses connect are masterpieces of tool-assisted engineering. The marks show that masons carved the contact surfaces to create a tight, friction-locked fit, a joint that could flex slightly under wind load and thermal expansion without cracking. This intricate stone puzzle, assembled with tools that created perfect fits, is a primary reason these buildings have survived earthquakes and storms for nearly 1,000 years. What do these integrity-focused marks tell us about medieval safety standards? They reveal a profound, pragmatic wisdom. A collapsed building was not just a financial disaster, it was a spiritual catastrophe and a loss of human life. The guilds, therefore, developed a culture of risk mitigation. Their tool marks are the legacy of that culture, a silent code of safety written in stone. They knew that the right mark in the right place, made with the right tool, could mean the difference between a monument for the ages and a pile of rubble. This was a technology born from the sober understanding of consequence, a forgotten science of stability that we are only now learning to fully read. The medieval workshop was full of tools that simply vanished. We have the marks they left in stone, clear and undeniable, yet the physical objects themselves are almost entirely absent from the archaeological record. This profound absence is our 22nd piece of evidence, a silent gap that speaks volumes about the materials they used and the realities of their world. Why have so few of these sophisticated implements survived the centuries? The most likely answer is also the simplest. They were made from organic materials that returned to the earth. Think of the complex frame that guided a saw to make a perfectly straight cut. Its intricate joints would have been crafted from wood, a material that rots away to nothing. The drive belts for a polishing wheel, the stabilizing cords for a drill, the entire body of a massive lifting crane, all would have been fashioned from leather, hemp, or wood. These were not primitive choices, they were pragmatic ones, using readily available, renewable resources to create complex machines that left behind only their ghostly impressions on stone. Some of the most intriguing theories arise from the marks themselves. On certain soft alabaster carvings, for instance, we find very fine, shallow grooves with a distinctive rounded cross-section. These marks lack the sharp, hard edge left by an iron chisel. Researchers propose that for this delicate work, artisans might have used tools made from bone or from specially hardened wood, materials that could be sharpened to a fine point and would be less likely to fracture the brittle stone. These organic tools would have been consumable items, sharpened and resharpened until they were worn down to nothing, then discarded without a trace. Another compelling idea is the culture of recycling. Iron was valuable. A broken chisel was not thrown away. It was taken back to the blacksmith's forge, heated, and hammered into a new tool, perhaps a nail or a bracket. The original object ceased to exist, its metal essence living on in a new form. This cycle of reuse means that the very tools that shaped a cathedral were likely repurposed over and over, their final forms bearing no resemblance to their original function. This mystery of the vanished tools forces us to think more creatively about what technology really means. It was not always about forged steel and complex gears. Sometimes it was about a brilliantly designed wooden jig, a tensioned leather strap, or a bone needle used to scribe a perfect circle. The loss of these objects to time does not make them less advanced. It simply reminds us that the most elegant solutions often leave the faintest footprints, challenging us to see the ingenuity in the empty space they left behind. A prayer book's margin glitters with gold leaf, but the real treasure lies in the humble scene painted beside the text. Here, a medieval artist has captured a mason at work, his chisel poised against a block of stone. This is our 23rd evidence where the illuminated pages of manuscripts become unexpected archives of technology. These illustrations, found in works like the Luttrell Psalter, offer a direct window into the medieval workshop, showing us tools in the hands of the people who used them. We see the bow of a drill being pulled back and forth, the posture of a carver leaning into his work, and the organized chaos of a building site. Yet we must read these images with a careful eye. The artist's goal was not documentary photography. He might exaggerate the size of a tool for emphasis, simplify a complex mechanism for clarity, or even omit crucial details to keep the composition beautiful and balanced. The depiction of a saw, for instance, might show its general form but leave out the specific frame that guided it, because that technical nuance was not important to the story the image was telling. How reliable, then, are these beautiful records? Their true value emerges not in isolation, but when they are held up against the physical evidence. Look at an illustration of a drill equipped with a crank handle. For a long time, this was seen as artistic license, but when we find those perfectly cylindrical, symmetrical bore holes in actual stone, the image transforms from a stylized picture into a plausible explanation. The art gives a name and a form to the ghostly machine implied by the mark. These manuscripts enrich our interpretation by adding the human element that the silent stones cannot. They show us the choreography of labor, how a team coordinated around a massive block, and how tools were held, carried, and maintained. A tiny detail in a background, like a tool chest or a workbench, can suggest the level of organization within a workshop. The combination is powerful. Archaeology gives us the what, the hard data of the mark itself. Art gives us the how, a potential method for creating that mark. Together, they allow us to reconstruct not just a tool, but an entire process, a fleeting moment of creation frozen first in pigment and then confirmed in stone. The tool marks on an English cathedral tell a different story than those on a French one. This is the 24th evidence, a map of technological diversity written in stone across Europe. In England, the grand perpendicular Gothic style is defined by strong vertical lines and vast windows. The tool marks that created this look are often deep, repetitive, and systematic, reflecting a tradition of efficient, large-scale production to meet the demands of a powerful, centralized church. Just across the channel, the French flamboyant style is all about flowing, flame-like tracery. The marks here are finer, more varied, showing a greater emphasis on individual artistry and complex, free-form carving. This is not a difference in skill, but a clear reflection of local priorities and the tools developed to meet them. Geography and culture were the invisible architects of these tool kits. Look at the rough-hewn, powerful chisel scores found in the granite churches of Scandinavia. The local stone was hard and difficult to work, and the marks reflect tools built for endurance and brute force over delicate refinement. Contrast this with the almost silky, polished surfaces of an Italian palazzo, where softer marbles and a culture valuing classical beauty led to the development of an entirely different set of finishing tools. The availability of materials directly shaped these choices. A region with access to high-quality iron ore could produce harder, sharper chisels that left cleaner marks. An area rich in fine abrasive sands could develop superior polishing techniques. The movement of artisans also played a crucial role. A master mason traveling from one region to another would carry his personal toolkit and his distinctive technique, leaving a foreign signature on local stone and slowly blending technological traditions. Historical climate and politics left their own subtle impressions. In politically stable regions with long-term building projects, we see remarkable consistency in tool marks over decades, suggesting established workshops with standardized practices. In areas of greater conflict or hardship, the marks can become more erratic, a physical record of disrupted trade in materials, the loss of skilled labor, or the urgent need to build quickly with whatever tools were at hand. What do these regional dialects of technology tell us about how innovation spread? They show that progress was not a single wave moving from one center to the periphery. It was a mosaic of local solutions, a web of interconnected but distinct developments. A clever tool design might emerge in a German town, adapted to local sandstone, while a different solution for the same problem was being perfected in Spain, tailored to its own granite. This geographic lens reveals a medieval world not of technological uniformity, but of brilliant, localized adaptation, where every valley and every quarry could produce its own unique answer to the eternal challenge of shaping stone. A digital ghost now haunts the ancient chisel mark. Researchers are using high-resolution, three-dimensional scanning to create perfect virtual replicas of these stone surfaces, models so precise they can be rotated in virtual light and analyzed in ways the physical stone would never allow. This is the 25th evidence where artificial intelligence and advanced imaging are becoming the ultimate tools for deciphering the past. Through a process called photogrammetry, hundreds of overlapping photographs are stitched together by a computer to build a map of a surface with microscopic accuracy. Once a mark is digitized, machine learning algorithms can be trained to recognize patterns that are completely invisible to the human eye. These systems can scan thousands of marks across an entire cathedral wall, identifying subtle clusters and variations that would take a lone researcher a lifetime to find. An ongoing project at a university laboratory is using this technology to trace tool wear trajectories. The eye analyzes a long, continuous saw cut, detecting tiny, gradual changes in the groove's width and depth. This data can reveal the story of a single work session, showing the precise moment a saw blade was sharpened or replaced, and even suggesting the level of fatigue in the worker as the day progressed. This is not just about the tool, it is about the rhythm of the workshop itself. In another case, high-resolution scans of a complex carving revealed a startling sequence. The digital model showed that the initial rough outline was made with one type of chisel, but a different, finer tool was used for the detailed work. More fascinating still, the scan detected a third, unique set of micromarks used only for the final polishing phase. This single piece of stone now tells a clear story of a three-stage production line, each step handled by a different level of craftsman using a specialized part of the toolkit. How will these advancements reshape our most basic historical interpretations? They transform individual marks from static clues into dynamic data, points in a much larger story of workflow and organization. We are no longer just looking at what was built, but at how the community of builders operated, how they managed their resources, and how they structured their day. The future of this analysis promises to uncover even deeper secrets, perhaps one day allowing us to digitally simulate the exact pressure and motion needed to create each mark, effectively resurrecting the lost tool and the hand that held it through the silent language of data. The principles perfected in medieval stonework offer a quiet blueprint for our own future. Those template-based cutting systems and precisely interlocking joints were not just about speed, they were a profound form of sustainability, minimizing wasted material and human effort in an era of scarce resources. Today, as we grapple with the environmental cost of modern construction, these forgotten efficiencies hold urgent lessons. Imagine applying that same mindset of resourcefulness to contemporary building, using advanced digital design to create components that fit together with medieval precision, dramatically reducing offcuts and industrial waste. This is not about abandoning technology, but about remembering a philosophy where every cut had purpose and every stone was valued. Restoration experts working on ancient monuments are already relearning these lessons, discovering that the traditional dry stone walling techniques, guided by centuries-old joint marks, create structures that are naturally flexible, self-draining, and incredibly durable without a drop of cement. This historical knowledge is inspiring a new wave of low-tech, high-performance design focused on resilience rather than brute force. Engineers are exploring how the passive cooling principles inherent in thick stone walls and the structural wisdom of keyed arches could be adapted for modern, eco-friendly materials, creating buildings that use less energy to heat and cool. The past whispers that our most elegant solutions may not always require more power, but rather a deeper understanding of form, force, and material. What if the path forward is found by looking back, by reassessing these lost technologies not as curiosities, but as a vital bridge between enduring history and necessary innovation? These silent scratches are far more than historical footnotes. They are a testament to a lost age of innovation, where human ingenuity met the unyielding resistance of stone and wood. This journey across centuries reveals that our ancestors were not primitive artisans, but brilliant engineers and system thinkers. They did not just build with what they had, they invented what they needed, creating specialized tools and repeatable processes that turned impossible visions into enduring reality. The evidence is all around us, not in grand declarations, but in the quiet language of a perfectly straight cut, a symmetrical drill hole, and a seamlessly interlocking joint. Each mark challenges the myth of a simple past and invites us to see these structures for what they truly are: complex machines born from a sophisticated understanding of physics, material science, and collaborative work. This reassessment does more than correct the historical record. It offers a powerful lens for our own time, reminding us that elegance often lies in efficiency, and that the most sustainable solutions may be those refined by centuries of practice. The next time you walk past an ancient wall or stand beneath a cathedral vault, pause for a moment, look closely at the stone. Let your eyes trace the lines left by tools and hands that have been silent for hundreds of years. What other stories are waiting in plain sight, whispering of forgotten technologies and the timeless drive to create? Your perspective is part of this ongoing discovery. Share what you have noticed in the comments below, and if you want to continue unraveling history's hidden narratives with us, subscribe for more journeys into the past. Together, we ensure that the legacy of these master builders is not lost but remembered and celebrated.